along the way. The first awardee is Dr. Alex Kwan from Cornell University, and he'll be telling us about his research focused on psychedelics as potentially novel, rapid-acting antidepressants, a topic that has received really feverish attention in the last few years. Alex, please join us.
Thank you. I'm excited here to be with you all in this beautiful location, and I'm glad that all of you are supporting mental health research. So in the next 10 minutes, I'll give you a brief overview of my research program. But if you have any questions, feel free to come up to me, ask me a question later today. I'm very excited about this research. In my lab, we're fascinated by how psychoactive drugs work. We're very curious how these small molecules can cross the blood-brain barrier, enter the brain, and then changes the structure and function of neural circuits, and thereby profoundly change the behavior in humans. One of our long-term goals is to be able to take some of these basic understandings and mechanisms to be able to start predicting how new molecules might work. So we take some new drugs, can we learn something about what it'll do to neural circuits and then also predict its behavioral effects? Within this context of drug research, my lab over the last several years have focused significantly on this molecule here, psilocybin. Psilocybin can be found naturally in the so-called magic mushroom, and there are over 1,000 species of the psilocybe mushroom that contain psilocybin. This is one of them, the psilocybe mexicana, which can be found in Mexico. And you might know the magic mushroom or psilocybin by its acute behavioral effects. So within the order of 3 to 4 hours, it has behavioral effects, and this is one excerpt from a woman who's been administered psilocybin. This is a drawing that she made after, and she also wrote this text, which I'll read now. My inner vision became the universe, filled with colorful waterfalls, glistening like stars, not bound by gravity. They floated in the air and folded around each other, totally quiet. The streams were infinite and beautiful. So this type of changes in the visual perception, as well as the colorful imagery, and the feeling of connectedness with the universe, or so-called mystical-like experience, is quite typical after receiving a psilocybin administration as an acute behavioral effect. Although more recently now, there also seems to be some evidence now for longer-term potential benefit for treating mental illness, which has now become quite exciting for the field of psychiatry. So these come from work from clinical trial at Imperial College London, at Johns Hopkins, also by Compass Pathway, phase 2 clinical trials showing that 1 or 2 doses of psilocybin, sometimes with assisted psychotherapy or psychotherapy, can lead to notable decrease in depression score when you give it to a patient with depression. What's notable, though, is that if you now compare it to what's currently available, placebo-controlled, people that did not receive anything, or fluoxetine, which is commonly known as Prozac, which is given on a daily basis, you see that the effect of psilocybin, at least in these early trials, is much quicker to act, and also is much more sustained. So again, there's just a lot of excitement in this field on using psychedelics like psilocybin for treating mental illnesses like depression. So within this context, my lab has been quite interested in understanding, given these interest in psilocybin, how the molecule works and what does it do to the brain. So before I get in there, I have one slide as a background. So this is a cartoon of a neuron. In the middle, you see the cell body, and then there's this beautiful dendrite that comes up with a little knob. Those are the dendritic spines. And these dendrites and dendritic spines are extremely important for the neuron because this is where how neurons communicate with each other. You may see this other red line coming in. That's another cell making that synapse, making that connection. So the dendrite and the dendritic spine serves to receive and integrate and process the information. And over the last couple of decades, there's a number of labs that show that in a control animal or in a healthy human being, you have these, again, beautiful dendritic tree. But if in animals that have received chronic stress, which is a key predictor of depression, or in human with depression, you start to see a loss of dendritic material. So one of the first things that my lab did was to start asking, how might a drug like psilocybin affect the dendrite in the brain. So to do that, we study mice, and we use a method called laser scanning optical microscopy, which I'm assuming most of you don't know what that looks like. So I took a couple of photos of my lab, and this is how my lab looks like. On the bottom left is two of the lasers that we use. These are called femtosecond laser. On the right is the laser scanning microscope. And if you come to my lab and actually look with these microscope, this is the kind of image you can get from the mouse brain. On the left is the dendrite. You can see those, again, I think it's gorgeous dendritic branches with the dendritic spine. And on the right is the reconstruction of that dendrite tree from the side view. You can, again, see the cell body and how this dendrite go up towards the top of the brain. So using these methods, we can track these neurons in a live mouse brain before, during, and after they receive psilocybin. But before we do that, one thing we have to find is like, what is the right dose to test? You can't really give the drug to the animal, a mouse, and then ask, did you have a psychedelic trip, right? Or did you have a colorful imagery? So instead, what we did is we tested a range of doses, and there's a very classic response that if you give a dose of psychoactive dose to mice, they start to twitch their head very rapidly. So you can see here on the mouse on the left receive a 1 mg per kg dose, and you can see that head twitches quite rapidly. So we know that this is a good psychoactive dose for the mouse. So now going back to the imaging, when we ask the question, how might this one dose of psilocybin affect brain structure, we tracked it over days, and what we found is that one dose of psilocybin lead to an increase in the number of these dendritic spines, which again reflect the number of neuronal connections in the brain. And this is done in the frontal cortex, the front of the head, which is related to our prefrontal cortex. So we can track these things over days. So here show we a plot showing that we can see this 10% increase in the number of neural connections the day after, and it's sustained in the mouse head for the last time when we looked, which is a month later, which was quite unexpected for us, how long-lasting this effect is, given that one single dose. So in the remaining time, I'll tell you a little bit about what we'll do in the future. I'm especially grateful for the One Mind Rising Star Award, which I think will enable us to make some important discovery in this area. As I mentioned, one of the mysteries, I think, for psilocybin is how come you have these acute behavioral effects that the trip and then the drug is washed out of the body quite quickly? How does it have these long-lasting potential benefits for mental illnesses? And our findings suggest that perhaps this dendritic reorganization of the neuronal connection could be quite important because the time scale is also very long. But one logical question that you might ask is, okay, if it has more connection, then what brain regions are these connections spanning? So what kind of specific pathways are being targeted and strengthened by psilocybin? So with this award, one of the goals is to try to use multiple different methods, optical methods, electrophysiological methods, to try to ask, given these neural connections, what are some of the inputs that comes in? Are they from other areas in the cortex? Are they from other regions like the amygdala or thalamus? And we might take a step back also and ask, then why is it important now if we can identify these pathways that are being selectively targeted by psilocybin? What might that be good for? One thing that we're excited about is if we know what brain circuit is being activated by psilocybin, we can potentially discover new molecule that might either target the same pathway or perhaps do the same thing but without some of the side effects. Another, I think, fairly exciting possibility is you can also think of some modulation strategy where you can have psilocybin in conjunction or maybe being replaced by some other methods that target these pathways to potentially augment the effect of some of these medicines. So with that, I want to say, I think psychedelic is now just being discovered as a very promising potential medicine for treating mental illnesses. But yet we still just don't know much about how it acts on the brain. So I think some of these basic science, like the one that I'm doing, I'm very excited on bringing some of these discovery to be able to translate the medicine into clinical use. Thank you.
We do have time. We do have time for questions. Please don't be bashful. Raise your hand.
Yes, and this is a very amateur question, but why can't you use human instead of mice?
Yeah, no, that is a good question. I think for mice, I think one advantage of mice is we can use some different methods in order to study the brain. So some of these methods to image it with a laser is rather invasive, so it's not approved for humans. So I think it allows us to get a much higher resolution on how the brain looks like. Yeah.
Let me just say also that in the experiments that Alex has done, this involves drilling a hole in the mouse's head and looking at microscopic features of the nerve cells. And the brain imaging techniques that we have for humans don't yet have that resolution. One day they will, but not yet. I do see other hands. I'm going to give the microphone here, but if we can get another microphone on this side of the hall, please.
Yeah, thank you. I'm just looking at the picture over here, and I'm wondering, all of those, the blue and the green little images seem to be on a certain part of the brain on the right-hand side. Is that because the psilocybin is going to certain parts of the brain only, or is that just the part of the brain that you're looking at?
Yeah, so the specific connection that we found was increased was in the front of the brain, the frontal cortex of the mouse. And here what this illustration shows is from tracing that people have done of different neurons that send input into that area. But you can see this one brain region received very diverse input from many other areas. Some of them receive input from multiple areas. So it's our job to try to disentangle this and figure out which of these specific pathways targeted by the psilocybin.
So
Go ahead.
congratulations on your award and your research. I'm curious about the clinical applications of psychedelics, and mental health already has kind of an unnecessary stigma around it, and so do psychedelics. Are you concerned that that might impede sort of their clinical acceptance down the road?
I think as a scientist, I believe in evidence. So I look at the phase 2 clinical trial and the upcoming phase 3 clinical trial, for example, by Compass Pathway and others. I think those would be a good indication eventually on the gold standard on whether some of these molecules could be useful for treating mental illnesses. And I think, yes, I should say that currently phase 2 clinical trial, promising result, but on the order a couple hundred people. And so there will be a larger trial, and I think that would be really demonstrating the efficacy potentially.
Ed.
First, I can address the question and comment. So I think the psilocybin and other psychedelics hold a lot of promise, as you said. There's a lot of interest in making sure that things are done correctly in the right environment, so the right supervision, so very effective treatment doesn't suffer the stigma, because the question was well taken, and that's one of the things that people are really trying hard, including the regulators, to make sure this is done appropriately so that there isn't a stigma. Congratulations on your data, and just a question. As you know, some NMDA antagonists have been shown to have rapid antidepressant effects, and in those cases it looks like by working on GABAergic interneurons you facilitate glutamate release, AMPA signaling, BDNF, and then the spine density changes. My understanding is that at least in the prefrontal cortex, the 5-HT2A receptors do facilitate glutamate release. And so just wondering whether whether AMPA throughput is necessary for the spine density changes.
I'll be happy to talk about that question.
Okay.
But it's a deep question. I think I can talk about it for 15 minutes. I think, I should do that offline. But I do want to, you mentioned at the beginning about how I think the context is important and that administration. I think that's why it's important to have these molecule, if we're going to be a medicine, to be administered in a regulated setting. So I think in the clinic where you have professionals, so I think that makes a big difference, and also with the psychotherapy and the preparation and the integration that goes into it, that I think is an important part that is part of for these medicines.
Go ahead. Just talk into it.
Real short. Your graph showed a 30-day period of change in dendritic growth. Does that repeat for an individual subject if you do it again over time, like for the next month, or do you repeat that? Just to see if the data, if the changes are consistent across?
Yeah, so that plot is actually from the same mouse that we could image before and then also after the single dose of psilocybin administration. And subsequently, we also actually have now some unpublished data where we extend out to 2 months, and we actually still see that density increase. We haven't done longer than that, but it's an open question on how long it stays. And I think the mechanism for how some of these new dendritic spine could stay for so long is also an open question.
Very nice, Alex. Thank you again.
Thank you.